Can you make it across the finish line when every step depends on your last? Jump Game is a Pattern Mastery 100 favorite and a classic at Google, Facebook, and Amazon, testing your greedy algorithms and array reasoning. 30% of candidates trip over edge cases or inefficient DP. Master this, and you'll breeze through reachability and greedy interview problems. Let's solve Jump Game using the basic approach, your step-by-step strategy for any reachability or greedy challenge. Given an array of non-negative integers, where each element represents your maximum jump length from that position, determine if you can reach the last index. List of integers nums, max jump at each index. Boolean. True if you can reach the end, else false. Picture crossing stepping stones in a river, where each stone tells you how far you can jump ahead. Interviewers might ask, how would you check if a player can always reach the end in a game with varying step sizes? What's tricky? DP is possible but unnecessary. Greedy works better. Watch out for zeros in the array, they can block progress if you can't jump past them. Must always keep track of the farthest reachable index. Initialize a variable farthest to 0. Iterate through the array. If the current index is greater than farthest, you're stuck, return false. At each index, update farthest equals max farthest, I plus nums I. If farthest ever reaches or exceeds the last index, return true. Initialize farthest equals 0. Loop over nums with index I. If I greater than farthest, return false. Update farthest equals max farthest, I plus nums I. If farthest greater than equals len nums, 1, return true. If loop ends, return false. Let's try to implement it using solution 1. Time complexity is O(n). Space complexity is O(1). This solution uses a greedy strategy. Instead of trying every possible jump, we track one powerful piece of information. We track the farthest index we can currently reach. As we scan from left to right, each position is either reachable or not reachable. If it is reachable, we can use its jump power to possibly extend our reach. If it is not reachable, we are stuck and must return false. If at any point our farthest reach gets to the last index or beyond, we can return true immediately. We start by setting reachable to 0. That means the farthest place we can reach at the beginning is the first index. We also store n so it is easy to check when we have reached the end. Now we walk through each index. The key check is simple. If our current index I is beyond what we can reach, then we have hit a gap. We cannot even stand on this position. That means we cannot move forward at all. In that case, we immediately return false. If we can reach index I, we use it to update our farthest reach. From I, the farthest we can jump is I plus nums at I. We keep the maximum value we have seen so far. We do that because we always want the best possible reach moving forward. After updating reachable, we check if it is at least the last index. If it is, we do not need to keep scanning. We already know it is possible to finish. So we return true right away. If we finish the loop without ever getting stuck, that means every step we needed was reachable. So the answer is true. And that's how this algorithm works. It first sets up a variable to track the farthest reachable position. Then it scans forward updating that reach greedily and fails fast if it hits an unreachable index. Efficient, simple, and elegant. Test case check, Jump Game using greedy reachability. Let's test our function using this input. 2, 3, 1, 1, 4. These numbers represent how far you can jump from each position, and our goal is to determine whether we can reach the last index. Here's why the solution works. We track the farthest position we can reach as we move through the array. If at any point our current index goes beyond this reachable range, we know we're stuck. Otherwise, we keep expanding the reach by taking the maximum of the current reachable distance, and the new jump range from the current index, I plus nums I. And that's exactly what our program outputs, true. The result matches the expected value, confirming that the greedy reachability method is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether we can reach the final index by tracking the maximum reachable position, efficient, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is O(n) squared. Space complexity is O(n). This solution treats the array like a graph of reachable positions. It uses BFS, which stands for breadth first search, to explore it. Each index is a node. From index I, you can move to any index from I plus 1 up to I plus nums at I. BFS explores all reachable positions layer by layer. The moment we reach the last index, we return true. To avoid revisiting the same index repeatedly, we keep a visited set. We also use a head pointer instead of removing from the front of a queue. That keeps queue operations efficient. First, we set up BFS. We start at index 0. So we mark it as visited. And we push it into a queue. The visited set prevents us from adding the same index multiple times. And the head pointer lets us read from the queue without slow operations. This loop keeps running as long as there are positions to explore. We take the next index from the queue. Then we immediately check one thing. Is it the last index? If it is, we have proven the end is reachable. So we return true right away. Now we explore every possible next step from the current index. If nums at I is 3, we can try jumping 1 step, 2 steps, or 3 steps forward. Each next index that stays inside the array and has not been visited yet gets added to the queue. That is BFS in action. We keep expanding the set of reachable positions. If we run out of things to explore and we never hit the last index, that means there is no path to the end. So we return false. And that's how this algorithm works. It first sets up a queue in visited set starting from index 0, then it performs BFS by exploring every reachable jump from each index until it either reaches the last index or runs out of options. Efficient, simple, and elegant. Test case check, jump game using BFS search. Let's test our function using this input. 3, 2, 1, 0, 4. These numbers represent how far you can jump from each index, and our goal is to see whether we can reach the last position in the array. Here's why the solution works. We treat each index like a node and perform a BFS search. Starting from index 0, we explore every reachable next position using all valid jump distances. We also track a visited set so we never recheck the same index. And that's exactly what our program outputs, false. This matches the expected value, confirming that our BFS exploration correctly detects when the last index cannot be reached. Wrap-up. So, our implementation is correct. The algorithm successfully checks all reachable paths using BFS and accurately identifies when the end cannot be reached. Efficient, accurate, and reliable. Jump game. Let's do a recap. So, we've just tackled one of the most popular reachability problems in interviews, jump game. It's fast-paced, logical, and a great way to show that you understand how to balance dynamic programming ideas with greedy reasoning. Once you grasp this, you'll spot the same pattern in dozens of real-world and interview problems. Breakdown recap. At its core, the problem asks, can you reach the end of an array if each element tells you how far you can jump? It's like stepping across stones. Every number tells you how many stones ahead you can move, and your goal is to make it to the last one without getting stuck. Assess recap. We compared two approaches, dynamic programming and greedy. While DP works, it's unnecessary here. Greedy logic is more efficient. The key insight was simple. Keep track of the farthest point you can reach. If at any point your current index goes beyond that limit, you're stuck. Otherwise, you keep pushing that boundary forward. Structure recap. We structured it around one core loop, moving through the array while tracking the farthest reachable index. If the current position is ever out of reach, we stop. If we extend the farthest reach to or beyond the final index, we've made it. It's clean, linear, and effective. Implement recap. We ran the greedy logic step by step on LeetCode. The code executed perfectly, no runtime errors, no boundary issues, confirming that the logic holds even with tricky cases like zeros and single-element arrays. Check recap. All test cases passed. The algorithm successfully determined when the end was reachable, and when it wasn't. It handled small, large, and edge cases exactly as expected, efficient, reliable, and consistent. Closing insight. The key takeaway? Jump game teaches you how to think ahead, literally. It's not about every step, but how far you can go from each one. Mastering this greedy mindset will help you tackle a whole class of problems built around reachability, optimization, and forward-thinking logic.